Hey everybody, in Calc BC, welcome to 7.5 Taylor's Series Part 2. We're going to be continuing our conversation today about Lesson 10.14 from College Board, Finding Taylor or Maclaurin's series for a function. We're going to dig into some more of the essential knowledge within these topics. We've already talked about how a Taylor polynomial for f of x is a partial sum of the Taylor series for f of x. We've also now talked about the Maclaurin series for sine of x, cosine of x, and e to the x provides a foundation for constructing the Maclaurin series for other functions. That's really what we're going to be expanding on today. I believe on another day, we will be talking, in another lesson, we'll be talking more about the series 1 over 1 minus x and how that's going to help us. So let's move into the notes. All right, so here's the question we're going to be answering today. Why do we care about finding a Taylor series for a particular function, such as the problems that we did in the previous lesson? For instance, why is it important to know that we can write sine of x equals x minus x cubed over 3 factorial, etc.? Trig functions lack finite algebraic formulas. Power series are the next best thing. Using power series allows us to find approximate but very accurate values of trig functions as well as other transcendental functions. So let's think about this before we even evaluate example A. Let's just think about the sine of 1. If I told you that without using a calculator, I wanted you to approximate the sine of 1, what would you do? I can tell you what I would do. I thought about this a little bit already, but I'm thinking 1 radian is about almost a third of the way to pi radians, right? Because pi would be 3.14 radians. So 1 is going to be somewhere near pi over 3. So if I'm thinking about my unit circle, I'm thinking, okay, we're like pretty close to pi over 3 if we're at 1 radian. And the sine is the y value of the ordered pair for thinking back to pre-calc. So I'm thinking root 3 over 2 is probably a decent approximation of the sine of 1. It's probably, I think the answer would be a little smaller than that because our angle is going to be a little smaller than that angle. But that's as close as I can get, I think, without a calculator. But I'm wrong. Now that we know about Taylor series, we can get a very accurate approximation of sine of 1 without using a calculator. So let's try this in example 1A here. So we're going to use the Maclaurin series for sine of x, which we have written right here. We're going to use that to approximate sine of 1 so that the error in our approximation is less than 1 over 1,000. We're going to do this without using a calculator. We're going to justify that the error is less than 1 over 1,000. So let's think about this. We have sine of x. Let's make this sine of 1. So I'm going to just start plugging in 1 for all the x's. So we have 1 minus 1 cubed over 3 factorial plus 1 to the 5th over 5 factorial minus 1 to the 7th over 7 factorial. We might need more terms, so I'm just going to leave it like that for now. And if I'm going to evaluate, I'm going to get 1 minus 3 times 2 is 6. This is going to be 1/6. 5 times 4 times 3 times 2 times 1 is 120. And then if I multiply 120 times 6 times 7, I'm going to get 1 over 5,040. It might take you a little bit longer than that to multiply all of those numbers together if necessary, but we could do it without a calculator, right? So we are trying to find an error that is less than 1 over 1,000. And isn't this an alternating series? So the error is going to be equal to or bounded by the first truncated term or the first term that we leave off of our approximation. So if you're tracking with me here, 1 over 5,040 is the first term where the denominator is bigger than 1,000, which means the fraction is going to be smaller than 1 over 1,000 because our numerator is 1. So this is what we want to be our error bound. So this is going to be our approximation. So we could say the sine of 1 is approximately 1 minus 1/6 plus 1 over 120. And I don't even need to combine those. That is a perfectly valid answer. And hopefully it's way closer than our original guess of √3/2. We'll check it in a second. We also could say that our error, we know, is less than or equal to the absolute value of this fourth term here, which was 1 over 5,040, which is indeed less than 1 over 1,000. So that's meeting the criteria of the question. And we could write that this is because it's an alternating series. All right, so let's check this on a calculator. So let's say we want to know, we're approximating the sine of 1. So now that we have a calculator, we have the sine of 1. I'm in radian mode, so that's good. So we have the sine of 1 actually equals 0.84147098848 ... Our approximation, which was 1 minus 1/6 plus 1 over 120. What's that equal? 1 minus 1/6 plus 1 over 120. Not bad, right? We got 0.8416 repeating. So we got the first 3 decimal places correct. That's not bad. So let's see. We had initially said √3/2. So what's √3/2 from our unit circle? Okay, yeah. So our approximation from part A is definitely closer than just by guessing based off of the unit circle. That is good to know. So now we wanted to know the error in our approximation. So here's our approximation. Here's the actual. So we're going to subtract them. So I'm going to write that out in official notation. So we have the absolute value of the sine of 1 minus our approximation. And if you calculate this, you're going to get that our error is 0.0001958 ... which really is pretty good. You know, how crazy is that we can approximate sine of 1 without even using a calculator and get within 0.000195 ... of the correct answer. That's the kind of stuff that we can do with Calc BC, everybody. Crazy. Okay, let's keep going. Find, in series form, an antiderivative for sine of x squared, and then use it to approximate the integral from 0 to 1 of sine of x squared, so that the error in your approximation is less than 1 over 1,000. Okay, interesting. Well, first of all, what on earth is going on with no dx here? There definitely should be a dx at the end of that integral. My bad, but let's try this. So if we're starting with sine of x squared, we're going to be substituting in x squared for every x in this initial series. So let's start with that. So we have sine of x squared. I'm just going to put x squared for every x. So we end up with x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, etc. And the exponent's doubled, right? Because if we have x squared to the 5th, it means we're doing 2 times 5, so we get a 10. So then if we're going to integrate, I'm going to write this out with the t like we did in the previous lesson. So we're going to start with from 0 to x of sine of t squared dt, which just means we integrate. So we're going to have x cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial minus x to the 15th over 15 times 7 factorial, etc. Hopefully we won't need more terms than this, but if we do, we can come back and kind of add more to each step as we need to. But we know that we are now going to be plugging in 1 because we're going from 0 to 1. So in this next step, I'm going to just plug in 1 for all the x's. So we're going to end up with 1/3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus 1 over 15 times 7 factorial, etc. And if we multiply out these denominators, we're going to get 1/3. If we do 3 times 2, we get 6. So 7 times 6 is going to be 42. We're trying to get less than 1 over 1,000, so we're not there yet. We're at 42, not 1,000. We're going to keep going. All right, getting a little bit trickier now. 11 times 5 factorial. So we got to do 5 factorial and then multiply by 11. That's the part that might take a little bit of time if we're doing this by hand. But we end up with 1,320 if you multiply that all out, which, good news, we're not going to have to do 15 times 7 factorial because that is already bigger than 1,000, which means the fraction is less than 1,000. So right here we have our error, which is less than 1 over 1,000. And that means that this right here, the first 2 terms this time are going to be our approximation. So we end up with 1/3 minus 1 over 42. And part B, we want to use a calculator to find the actual error in our approximation. So if we do the integral from 0 to 1 of sine of x squared dx, we can use a calculator to figure that out, right? So let's try it. So we're going to have to go into the math menu and get a definite integral. We're going to go from 0 to 1 of the sine of x squared dx. And we're going to get 0.3102683.017. 3102683.017 ... And what's the value of our approximation? 1/3 minus 1 over 42. Pretty close. We get 0.3095238.095, etc. So if we subtract those to find the error, what are we going to get? 0.000744449, etc. Yeah, so the calculator shows it as times 10 to the negative 4 if you happen to see it like this. So that means you're going to make sure you need to move the decimal place 4 places to the left. So we have 1, 2, 3, 4. So 3 zeros and then the 7. Okay? All right, awesome. Let's keep going. Couple more questions here on the back. Write the Maclaurin series for f of x equals e to the x. Give the first 4 non-zero terms and the general term. Well, this should be easy for us. We already have this from our previous lesson. So e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That's the first 4 non-zero terms. The general term we defined as x to the n over n factorial. That's it. Part B, use your answer to find the limit as x approaches 0 of f of x minus 1 all over 2x. So we're saying that f of x is e to the x. Okay. So what if we, instead of trying to use, like L'Hopital's rule or something here, what if we just plugged in this Maclaurin series for f of x? Because right now, f of 0, it's 1 minus 1 over, so we get 0 over 0. So this is just kind of showing you how you can use series in limits. So we're going to demonstrate how to do that. So we have limit as x approaches 0. We're going to replace f of x with e to the x, which is now going to be this series. So it's going to be 1 plus x plus, I'm going to write the whole thing out like we have up there. And that's minus 1 all over 2x. So what's going to happen to this 1? Well, the first term in our series is 1, so we can do 1 minus 1, and that goes away. So now we have the limit as x approaches 0 of x plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. all over, why did I just write a 2? That should have been over 2x. And now we can actually distribute the divided by 2x to every one of these terms. So we're going to have the limit as x approaches 0 of x divided by 2x is going to be 1/2. In this second term, the x squared divided by x is just going to give us x, and an extra 2 is going to accompany the denominator. So we end up with x over 2 times 2 factorial. Then we have x squared over 2 times 3 factorial. And that's going to keep going. The general term is going to be what? X to the n minus 1 over 2 times n factorial. And what's going to happen as x approaches 0? All of these terms that have x's are going to go away and just leave us with that 1/2. Right? So that's generally how you can use limits and series together. We are going to do one more question here, which is going to be to write the first 4 non-zero terms of the Maclaurin series for f of x equals 8 e to the x times cosine of x. So we can actually multiply series together. And here's how we can do it. We have e to the x times cosine of x. I'm going to write out the first 4 terms of each of these. We might need more than that, but we'll see. So we have 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. times the series for cosine of x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. And so the idea is that we're multiplying these two series together, and we're trying to find the first 4 non-zero terms. Now, the terms are always organized by power, so it goes in order from lowest power to greatest power, which is most likely eventually infinity. So what we're doing here, you got to think about how we have to distribute every time we multiply. So this 1 is multiplied by this term, this term, this term, this term, all the terms. Then the x is multiplied by all of these terms. Then the x squared over 2 factorial is multiplied by all of these terms. So the idea is we have to find all of the multiplications, all of the pairs that multiply together to give us a constant. Let's start with that. So I believe if I multiply 1 times 1, that's the only time that we're going to get, no x's in our answer, right? So the first term is just going to be 1. That's 1 times 1. What pairings will give us just terms that have x to the first? Well, if I start with this 1 and start to distribute it, we get 1 times 1, and then the second pairing already has an x squared. So I'm not going to get any pairings with this 1 that give us an x to the first. What if I think about this 1 being paired with all of these terms? Well, 1 times 1 doesn't give me an x to the first. Aha, right here I have an x times a 1. So that's going to give us just an x term. And then as soon as I move on, we have an x squared already. There are no other pairings that give us x. So that's a 1 plus x so far. So now let's look for any x squared terms. So if I start with this one, I'm going to get 1 times x squared over 2 factorial. So that'll give me And that's negative, so that's going to be negative. And that'll give me an x squared term. If I start with this x and distribute, I'm not going to get any x squared terms. What if I start with this 1? Boom, boom, boom. Okay, I got an x squared over 2 factorial times a 1. That'll count. And I don't think I have any other pairs that I can match up to give me x squared terms. So we're stuck with that. And that's actually rather unfortunate because look, those x squareds are going to cancel. So we have no x squared terms. We're looking for the first 4 non-zero terms. So that means we're going to have to go further. So we got the constant term, the x term. That would have been the x squared term. So now we're going to look for the x cubed and the x to the 4th. All right, so let's just start with this and match it up. So we got 1, nothing's going to give us x cubed. If we start with the x and distribute, x times x squared is going to give us x cubed. So we have negative x cubed over 2 factorial when we multiply that. What if I just do the x squared? Nothing, x cubed times a 1. Okay, that's going to work too. So we have plus x cubed over 3 factorial. And lucky for us, that's not going to cancel. So we're good. We can keep that. That's still only 1, 2, 3. That counts as 1 term. So that's 3 non-zero terms. We got to go to the x to the 4th then. So I'm just going to start over here and try to match this up. So we got that works. X to the 4th over 4 factorial. If I match the x terms up, nothing happens. If I match the x squared, oh, I have an x squared and an x squared. That's going to give me x to the 4th, and it's negative. It's x to the 4th, and it's going to be over 2 factorial times 2 factorial. Because we got to multiply the terms together. All right, if I do x cubed, nothing. Okay, we've got an issue here, because if I go to the x to the 4th term, I'm going to be multiplying by 1 and getting an x to the 4th term down here. So let me write out what that term would be. It would be x to the 4th over 4 factorial times 1. So we are going to have that term there. Okay. And that's going to obviously keep going. There are no more terms that are going to give me x to the 4th as the x degree. So we've got 1, 2, 3, 4. You will see that this is often written with all of the x terms kind of like factored out. So I'm going to write it like that so it just looks like we have coefficients. So if this one is going to be what? Negative 1 over 2 factorial plus 1 over 3 factorial as the coefficient of the x cubed, like that. And then we'll do the same thing for the x to the 4th. So it'll be 1 over 4 factorial minus 1 over 2 factorial times 2 factorial is really wacko weighing of just writing 4, right? Because that just means 2 times 2. So I'm just going to write that as 4. And then we have plus 1 over 4 factorial again. And that's the coefficient of the x to the 4th term. And that's really as simplified as we need to get, right? I mean, we could go further and find out the actual coefficients, but we don't need to. So I'm just going to stop there. Okay. So hopefully that made sense. It's all about distributing each term. And yeah, so that's what we're going with here. There you go. That's your Taylor series. So thanks for watching. Have a great rest of the day. Let me know if you have any questions.